Welcome to this lecture. In this lecture we are going to discuss about the non-homogeneous wave equation, how to solve it using a very general principle called Duhamel principle. So, the outline for the lecture is as follows. First we recall certain things from the lecture 4.1, and then we state the Cauchy problem for the non-homogeneous wave equation. Then we introduce Duhamel principle after giving a motivation for it. Then we apply Duhamel principle to wave equation, we do for 1, 2 and 3 space dimensions. So, let us recall from lecture 4.1 certain things about the Cauchy problem for non-homogeneous wave equation. Okay. So, given functions phi psi and f, Cauchy problem is to find a solution to the wave equation. This is the D'Alembert operator equal to f on RD cross 0 infinity, such that u of x 0 is phi x, ut of x 0 equal to psi x. Phi and psi are generally referred to as Cauchy data and f is referred to as a source term. The D'Alembert operator is a linear operator, since D'Alembert applied to u plus v is D'Alembert acting on u plus D'Alembert acting on v. Therefore, a solution to the Cauchy problem which was stated on the earlier slide, that is the non-homogeneous wave equation with the Cauchy data, that may be obtained as sum of two functions v and v tilde, where v is the solution to the Cauchy problem where the wave equation is without the source term. Okay, it is called homogeneous wave equation. When there is no source term, it is referred as homogeneous wave equation, and v tilde is a solution to the non-homogeneous wave equation, but with 0 initial conditions. We will state more clearly on the next slide what the problem precisely is. So, u equal to v plus v tilde, and v satisfies this homogeneous wave equation and the Cauchy data, and v tilde satisfies non-homogeneous wave equation and 0 Cauchy data or 0 initial conditions. So, when you add v plus v tilde by the linearity of the D'Alembert operator, D'Alembert of u will be D'Alembert of v plus D'Alembert of v tilde, that will be 0 plus f, therefore f. So, you get the non-homogeneous wave equation satisfied by u, and then look at the first initial condition, v x 0 is phi x, v tilde x 0 is 0, therefore u of x 0 is phi x. Similarly, ut of x 0 is v t of x 0 plus v tilde t x 0, one of them is psi and the other one is 0, therefore the addition will be psi, the sum will be psi. So, therefore, u indeed satisfies the non-homogeneous wave equation. And recall that we have already analyzed these problems, the homogeneous wave equation and the Cauchy problem for it we have analyzed already. Therefore, it is enough that we analyze this or know how to solve this problem, then we know how to solve the non-homogeneous Cauchy problem for the wave equation. So, let us look at the Cauchy problem for non-homogeneous wave equation with homogeneous data or 0 initial conditions or 0 Cauchy data, and we want to solve this Cauchy problem in dimensions 1, 2, 3, because we are discussing only wave equation in 3 dimensions 1, 2 and 3. These are the 3 dimensions in which we are discussing wave equation so far. So, a general principle called Duhamel principle will be used. So, what is Duhamel principle? It says solutions to non-homogeneous linear differential equations, that is also known as equations with source terms, may be obtained as a superposition of solutions to the associated homogeneous differential equations. In other words, what it says, this is a rough statement, precise statement we are going to see later. If you want to solve non-homogeneous equations, it is enough to solve homogeneous equations, that is what it says. Of course, the initial data will be tailored using the source terms, because after all we want to solve the non-homogeneous equation, that means source term is given to us. So, we have to use that and make or manufacture this homogeneous differential equations and the corresponding Cauchy problem, essentially the initial data will be tailored using the source terms. Okay, motivation for Duhamel principle we will give using initial value problem for a second order linear ODE. So, initial value problem for a second order linear ODE is given by this d2y by dt square plus mu square y equal to ft, y of 0 is y0, y dash 0 is y1. So, in this f y0 y1 are given and we are supposed to find a solution to this ordinary differential equation satisfying these two initial conditions. If you notice, this looks like wave equation because in wave equation we have a u2t term, that is like d2u by dt square, but instead of mu square y we have minus Laplacian y, okay, equal to f of xt. Naturally, wave equation being an equation being a partial differential equation, you have both x and t variables, but one can view wave equation also as an ordinary differential equation. Here in an ordinary differential equation, y is a function of t, given any t y will be y of t will be a real number. In the wave equation, given any t, u of t will be a function of x, that is the difference. We will come back to this later. So, first let us see how Duhamel principle works in this example. So, the solution to the initial value problem one can explicitly solve and write down as this: y of t is y0 cos mu t plus y1 sin mu t by mu plus 1 by mu integral 0 to t sin of mu into t minus tau into f tau d tau. This is a formula one can verify. We are already used to this in a course on ODE, we would have got this solution. Now, we want to see each and every term closely and then we will see how Duhamel principle comes into play. So, before that let us introduce this homogeneous equation. Remember, Duhamel principle is something to do with the homogeneous equations now, where the, so we will make the equation homogeneous and the initial data has to be tailor made using this source term. Okay. So, with that view in mind, let us discuss homogeneous ordinary differential equation with initial conditions where y of 0 is 0, that is initial position is 0 and initial velocity is y1, y prime 0 is y1. A solution to this we will denote it as S y1 of t. So, S for solution, y1 to remember that y prime 0 is y1 and solution for this ODE, ODE is in the background, homogeneous ODE. And this map which maps given y1 a real number to this solution sy1 of t of this problem is called the source operator. And of course, we know the formula and that is given by y1 times sin mu t by mu. So, sy1 of t is the solution of this homogeneous ordinary differential equation and with y1 as the initial speed or initial velocity and initial displacement or initial position is 0. Okay. So, in terms of the source operator, the solution of the IVP is given by this yt equal to s y0 of t d by dt of that plus s y1 of t plus integral 0 to t s f tau t minus tau d tau. What is s f tau? It is a solution operator. What does it do? It maps f of tau as given as the initial velocity, s f tau of t will be the solution of the given ODE. Okay, let us define the integrand to be a function of t with the tau hanging around. So, w of t semicolon tau is s f tau of t minus tau. We will observe what happens to this w, what is that w satisfies. So, where each tau positive, the function w as a function of t is defined for t bigger than tau and it solves the ODE. So, it is a solution to the homogeneous equation and it satisfies initial condition. When you put t equal to tau, w will be 0 and wt of tau tau will be f tau. Remember, that is how the source operator is defined, right. Source operator is defined like that. When t is equal to tau, it is s f tau at 0. So, that is why that is 0, because SF tau solves with 0 initial displacement and this is the velocity. So, that is d by dt of this quantity at 0 will be F tau. Okay. Now, if you observe this first two terms, sum of the first two terms is a solution to the homogeneous ordinary differential equation, and the Cauchy data is satisfied, that is y of 0 is y0, y dash of 0 is y1 is satisfied. Now, this term essentially is solving the non-homogeneous ordinary differential equation with 0 initial conditions. And how is it obtained? As an integral. You can think integral is a certain sum, therefore generalization of the sum, therefore this is a superposition of the quantities inside. But what are the things inside? They are solution to the homogeneous equations. So, this is the explanation or the motivation of Duhamel principle coming from initial value problem for a second order linear ODE. Now, let us apply Duhamel principle to wave equation. So, wave equation as a second order ODE, one may interpret the wave equation as an ODE in the variable t. In the case of ODEs, for each fixed t, y of t is a real number or an element of Rd, depending on whether we are dealing with a scalar equation or a system of equations. In the case of wave equation, for each fixed t, u of xt is a function of x in Rd and thus takes values in space of functions defined on Rd. So, let us compute the source operator in the context of wave equation and construct a solution to the Cauchy problem for non-homogeneous wave equation. So, let us see what is the source operator for the wave equation. What is that? Si of t for the ODE, right? For the wave equation Si of xt. What is this psi represents? The initial velocity and initial displacement is 0 and you solve the homogeneous equation exactly as it was the case in ODEs. So, Si of xt, let it denote the solution to this Cauchy problem for the homogeneous wave equation and 0 initial displacement and initial speed as psi. The source operator is well defined. We have to ask when is it well defined, that means we have to ask when is that we have a classical solution to this. If d equal to 1, we need psi to be in C1 because we have a D'Alembert formula which is applicable, and then for d equal to 2 or 3 we need psi to be in C2, that is when the source operator is well defined. Now, we expect the function, this is precisely that sy0 dash, now it is y0 is phi and y1 is psi in the context of wave equation. This is sy1 and this is integral 0 to t s f tau, which we now wrote f subscript tau of t minus tau, x dependence is there, so we write that. So, this we expect to solve the non-homogeneous wave equation and the Cauchy data. So, f tau of x stands for f of x comma tau. So, we expect that to solve this Cauchy problem. Let us call this as a non-homogeneous Cauchy problem. Okay. So, we have to check that. So, in this formula, sum of the first two terms on the RHS, namely these two terms, is a solution to the homogeneous wave equation and satisfies the initial conditions. What are those? Initial displacement is phi and initial velocity is psi. So, these conditions are taken care by these two terms. Therefore, what we expect is this term will be a solution to the non-homogeneous wave equation with a 0 initial data. Okay. Now, remark on the first term. So, we have to check that these are indeed solutions to the homogeneous wave equation, we are going to do that and they satisfy the Cauchy data, we will check that. So, now let us concentrate on the first term, it is dou by dou t of s phi of x comma t. It is a derivative with respect to t of what? S phi of x comma t. What is s phi of x comma t? It is a solution to the wave equation by definition. Solution to the wave equation, homogeneous wave equation, initial displacement 0, initial velocity phi x. Now what we have, the first term is a time derivative of a solution to the homogeneous wave equation. Therefore, it is itself a solution, one can check that. If you have a homogeneous wave equation and let us say u is a solution to that, then dou E by dou t is also a solution. Dou k u by dou t k is also a solution. We have already mentioned this in one of the tutorials earlier, otherwise you can just check. So, it is a solution, that is not doubt. So, it follows from derivative of a solution is a solution for the homogeneous wave equations. Now, we have to check the initial data. So, this first term satisfies initial displacement phi and initial velocity to be 0. So, let us check initial displacement, that is dou by dou t s phi of x t at t equal to 0. We want to check this is phi x. This is by definition, because what is S phi? S phi is solving homogeneous wave equation with the initial velocity as phi. This is exactly that, dou by dou t of that is the initial velocity. So, that is phi. So, this is by definition. Now, we have to check this condition, initial velocity, is it 0 or not. That means, we have to take this term, differentiate this with respect to t, that means essentially dou 2 by dou t square of S phi and check that is 0. So, this is what we have to check, dou 2 by dou t square of S phi of x comma t at t equal to 0, compute what it is. By the equation, because it satisfies homogeneous wave equation, right. So, u t t equal to c square Laplace in u. So, that is what I have written, but now I will evaluate at t equal to 0, that is why both sides I put t equal to 0. Now, what is Laplacian? It is a differential operator with respect to x. What am I doing here? I want to take the value at t equal to 0, therefore, I can as well take the evaluate at t equal to 0 and then take the derivative with respect to the other variables, space variables, or take the derivatives and then take t equal to 0, both are same, because the evaluation I am going to make is for t and the derivative that I have in the front is Laplacian, that is with respect to x. Therefore, when I do that I get this, but what is S phi of x 0? By definition of S phi, the initial displacement it is, right, of the solution. So, therefore, that is 0, therefore, it is 0. Now, if you notice, instead of Laplacian you could have had any operator that does not depend on t. This is an interesting and important observation. So, the Duhamel principal application is not limited to wave equation only. You can apply u t t equal to any operator L of u as long as L does not involve the variable t. So, therefore, we check the first term satisfies homogeneous wave equation and it satisfies the initial conditions u of x 0 equal to phi, u t of x 0 equal to 0. Now, let us move to the second one, which is more straightforward because just the definition. The second term is by design or definition is a solution to the homogeneous wave equation with initial displacement 0 and initial velocity as psi, that is the definition. Therefore, the sum of the first two terms is going to solve homogeneous wave equation because both of them are solutions to the homogeneous wave equation, and initial conditions will be now u x 0 equal to phi and u t x 0 equal to psi. Done. Now, we have to concentrate on the third term now. What about the third term? So, the integral term satisfies 0 initial conditions because if you check t equal to 0, integral collapses, there is no integral, so it will be 0, and check that the derivative is also 0, that I leave it as exercise, very easy to check. So, what remains to really check is that this satisfies the non-homogeneous wave equation. Then we would have proved that this is a solution to the non-homogeneous Cauchy problem. Let us do this checking. So, first we have to compute the derivatives, right. If you want to check this is a solution to the wave equation, you have to compute 2 time derivatives and 2 x derivatives. Okay, let us compute the first derivative, dou by dou t of this. Now, we are going to use Leibniz rule. Okay, whenever you have integrals which depend on the variable with respect to which you are differentiating, there is a rule how to differentiate that particular integral. I am going to follow that. So, therefore, you get this derivative equal to the inside thing evaluated at t tau equal to t, that will give you this, because tau becomes t sft x comma when tau equals t it is 0. So, you get this, plus you are going to differentiate inside the integral. So, 0 to t remains as it is and dou by dou t of the inside quantity. So, we have this. What is sft of x comma 0? It is 0 by definition. That is how the source operator is defined, and I have not changed the integrand as it is. So, one at a time. Now, let us differentiate once more. So, we use Leibniz rule for differentiation of integrals here, and it is actually a consequence of fundamental theorem of calculus and chain rule. SFT of x0 is 0 by definition of the source operator. So, first derivative of the integral term is this. Now, we will compute the second derivative. So, this is being carried forward from the previous slide. This is the first derivative of the integral term. Therefore, second derivative becomes first derivative of the first derivative. Now, exactly again by the Leibniz rule, this will be the integrand evaluated at tau equal to t plus differentiate inside with respect to t. This quantity is precisely f of x t, once again from the definition of the source operator. Now, here we see that dou 2 by dou t square of some solution, right. S of tau after all is a solution to the wave equation. Therefore, dou 2 by dou t square can be written in terms of the Laplacian. So, it is c square Laplacian of whatever is here, and Laplacian comes outside and we have this. Therefore, we have proved that this integral term satisfies dou 2 by dou t square minus c square Laplacian equal to f x t, right. Take this term to the LHS, then precisely we have this. That is, integral term satisfies non-homogeneous wave equation, and rest of this lecture is devoted to writing down the source operator explicitly in each of the dimensions 1 to 3 and obtain explicit formulae of solutions to the non-homogeneous Cauchy problems. Before that, let us give a remark on the integrand in the particular solution. Yeah, we may call this thing as a particular solution. This is a nomenclature that we use even in ODEs. It is one particular solution, that means it is one solution of the non-homogeneous equation. So, as before we already introduced this in the context of ODEs. So, integrand you call it as w of x t comma tau, then the function w satisfies homogeneous wave equation and it satisfies initial conditions when t equal to tau, w is 0 and the derivative of w when t equal to tau is f of x tau. So, in other words, you see this is a superposition of solutions to the homogeneous equation with initial data which is tailor made using the source terms. This explains Duhamel principle. So, let us obtain explicit expressions. We have already solved the homogeneous wave equation and Cauchy problem. So, it is just matter of writing down what the source operator is. So, by D'Alembert formula, the source operator S psi is this 1 by 2 c integral x minus c t to x plus c t psi s ds. So, solution to the non-homogeneous wave equation is this dou by dou t of S phi plus S psi plus the integral term 0 to t S psi of some t minus tau x tau dt, which is there on the previous slide. Okay, we can simplify this further and we get this expression, because here it looks a very complicated expression. We can use the Leibniz rule and get this expression. So, if you notice, the first two terms is precisely the D'Alembert formula. That means when f is 0, phi and psi, that is solution of the homogeneous wave equation and the Cauchy problem for that. And this is the new term which we have added to get solution to the non-homogeneous Cauchy problem. Now of course, we have to ask this question, when is it a classical solution, what are the assumptions needed. Of course, if you look at the formula, it is meaningful, this is meaningful if phi is let us say continuous, integral we need, therefore psi should be continuous, again some integral, so f should be continuous. But that is not enough. For classical solution we require phi in C2, psi in C1, we have already noted down this when we discussed the homogeneous problem for the one dimensional wave equation. Now what about this? Remember this f, this term how did we get? The f went into initial velocity in the definition of source operator, therefore we need some first derivative of f to be continuous. So f should be continuous, so that this makes sense. In addition, you need first derivative of f with respect to x to be continuous. Okay, that is what is needed to make sure that the source operator is well defined with this as the initial velocity. Done. Now the comment on the domain of integration in this integral, what is this? It is a triangular region formed by x axis and the two characteristics which are passing through the point xt. That is, if you look at this, take a point, this is the point x comma t. So this is the line which are going through, this is x minus, we should have used x naught t naught, then this is x minus ct equal to x naught minus ct naught, that is the line, and this line is x plus ct equal to x naught plus ct naught, and this is x axis. So this is the triangular region. Okay. If you see, this is where we plot x and t here. So, okay. So here this formula you just read it with the x0 t0, that is what I am reading, x0 t0, this is also t0. So this point is t0. You fix any thing in between, let us say t equal to tau, okay. Then you are going from this point to this point. This is precisely the 2 points here, this and this. Okay. So this triangle is called characteristic triangle. Now let us move on to the two space dimensions. By Poisson-Kirchhoff formula, the source operator is given by this formula, and now this is the expression dou by dou t of s phi plus s psi plus that integral. So we get this formula. Using a change of variable, it is convenient to write it on disk of radius 1 with center 0, the homogeneous equation part. Again same question, under what hypothesis it is a classical solution. No need to see, look at the formula, phi integral involved, so phi continuous, grad phi integral is there, therefore grad phi continuous, psi continuous, f continuous, we can put such conditions. But then we want a solution for which we need higher smoothness. Phi should be C3, psi should be C2, and f should be continuous, and also gradient should be continuous with respect to x, and the second derivative should also be continuous with respect to f. Reason is exactly the same as we gave for d equal to 1. This f is going to sit in according to the Duhamel principle, this f, the source term, will go to the initial velocity, and for initial velocity we need C2ness, that is why this condition. Let us move on to 3 space dimensions. Again from Poisson-Kirchhoff formula in 3 dimensions, Si has this expression, and therefore by Duhamel principle U has this expression. Now which values of f are needed to determine U at the point x0 t0, that is a question we ask. So we write the expression for U of x0 t0, of course f is not coming here, but if you ask what values of psi and phi are needed, it is clear that we need the values on the sphere of radius ct0 with center x0. What are the values of f which are needed? That is what we are asking here. So set of all y tau such that tau is here, y is here and tau between 0 and t naught. So, they are needed on this set. Now, what is y is here? Y minus x naught norm is c times t naught minus tau, c into t naught minus tau, exactly that. This is a sphere, y should belong to that and tau should belong to 0 to t naught, that is exactly what I have written here. But what is this set? This is a subset of R4, R3 cross 0 infinity. This is a backward cone with a vertex at x0 t0. We know the cone in 3 dimensions, right. So, this is something similar we have to imagine in 4 dimensions. I will show you a picture. In other words, the value of u at x0 t0 depends on the sources coming from the backward cone with vertex at x0 t0. So, figure of a backward cone is on the next slide, it is here. This is a point x0 t0, what we are used to when it is R2 in the plane and you have a cone. This is called backward cone or past cone, this is called forward cone or future cone. We will discuss about this in a future lecture more on this, but this is what is needed. The values of f are needed on this cone. Therefore, since y is in the sphere, that means that norm y minus x is c into t minus tau. The formula may be written like this, now t minus norm y minus x by c and norm y minus x. Earlier it was written t minus tau, but now that we can convert in terms of y and x. And if you just combine what you get here, that is precisely the ball of radius ct with center at x. So, the ball is written as a lot of spheres which are union, take the union or yeah. So, that is what you have. For each fixed tau you have a sphere and then take the union as tau varies from 0 to t. So, you get this. So, again the same question, when is this a classical solution to the Cauchy problem? Of course, formula is meaningful under some set of assumptions on phi, psi and f, but if you want a classical solution you need phi to be C3, psi to be C2 and f to be here continuous, f gradient to be continuous and second order derivative to be continuous on R3 cross 0 infinity. So, the value of f of yt for any y in this ball of x comma ct does not play any role in determining the solution at the point xt. On the other hand, the values of f of yt at the retarded time t, which is t minus norm y minus x by c, that is what they plays a role if you see the formula. And this situation is totally different for d equal to 1. I will request you to check what is that difference from 3D in 1D, and this integrand is called a retarded potential because instead of t we have t minus norm y minus x by c. So, justify the word retarded time after you learn about Newtonian potentials in the context of Laplace equation, which will be done later on. So, let us solve an example, solve a problem, Cauchy problem, non-homogeneous Cauchy problem. I have taken simple initial data because I want the computations to be simpler. Okay. Of course, we have already said this is a formula, okay. F is a smooth function, no problem. So, this will represent a classical solution because phi is smooth, psi is 0 and f is definitely smooth. You can compute directly by plugging in these values, we do not do that. What we do is we apply Duhamel principle directly. So, for the given Cauchy problem psi is 0 and therefore, the solution in terms of the source operator is given like this. Now, we have to find the source operator and that is given by this, by the D'Alembert formula, which we can compute, that is xt, S phi of x comma t is xt. Now, let us compute what is sf tau. By definition it is this given by this formula, and compute what is f tau of s, that is s into e power tau. Compute these integrals, you get t minus tau into x e power tau. Now, find this integral because this is what will give you solution to the non-homogeneous wave equation, and that is given by this integral. On simplification we get this formula, x e power t minus x t minus x. Now we have to add these two. Okay, dou by dou t of S phi is required. S phi was x t, so dou by dou t will be simply x, plus this we will plug in from the last slide. Solution is x into e power t minus t. So we have introduced Duhamel principle, applied it to obtain solutions to non-homogeneous Cauchy problems. We observed that the Duhamel principle works for any operators of the form utt minus Lu. For wave equation, L is the Laplacian. For what operators it will work is the operator L can be any differential operator not involving the variable t in it. Thank you.